Welcome to another session. My name is Mashire Nyaga. We are going to discuss about data and program representation. The previous chapter we introduced about, we discussed about the digital logics, and we described the basic hardware building blocks that are used to develop the digital system. We are going to continue to discuss the fundamentals by explaining how digital systems use binary representation to encode programs and data, and how the programmers view or understand the format that the underlying hardware use to improve the speed of computers. So we're going to go straight on to understanding the digital logics and the importance of the abstraction. The digital logic circuit contains many low-level details. The circuit uses transistors and electrical voltage to perform basic operations. The circuit uses transistors and electrical voltage to perform basic operation. The main point of these digital logics, however, is called the abstraction. Right? So, what is abstracting? It means that the complex digital systems such as memories and processors can be described without thinking about individual transistors or voltage. So, abstraction in a nutshell might be said, or we want to hide the underlying details and use the high level of abstraction whenever is possible. So when a computer architects use the logic gate to design computers, they do not think about such details. Instead, they use abstract designation for the logical 0 and 1 from the Bohr's algebra, right? So abstraction means that the complex digital systems such as memories, processors can be described without thinking about individual transistors. More important, abstraction means that a design can be used with a battery-operated device such as the smartphone, and that uses low voltage to reduce the power consumption. So to a programmer, the most important abstraction are items visible to the software, the representation used for data and programs. I think that's well captured. So we move on to understanding what's a bit and what's a byte. All data representation builds on the digital logic. We use the abstraction binary digit called the byte, or the smallest element in computing, to describe a digital entity that can have two possible values and assign the mathematical names 0 and 1 for the two values, right? So in anything, whenever we talk about a bit, we simply mean the logical number, the 0 and 1. Multiple bits are used to represent more complex data items. E.g., each computer system defines a byte to be the smallest data item, larger than a bit, that the hardware can manipulate. So, if you're asked, how big is a byte? The size of a byte is not standard across all computer systems. Instead, the size chosen by the architects who design the computers decide that, right? Depending on for example, the early manufacturers used a different design compared to whatever we currently have, right? So we move on to the bit size. The number of bits per byte is especially important to programmers because the memory is organized as a sequence of bytes. The size of the byte determines the maximum numerical value that can be stored in 1 byte. A byte that contains the contains the k bits can represent 2k values, exactly 2k unique strings of ones and zeros that exist in a length of k, right? So we move on. We can consider a possible combination that can be achieved with the 3 bits, and this should be the illustration. A 6-bit can represent a 64 possible. So what does a bit given pattern represent? The most important thing to understand is that bits themselves have no specific meaning. The interpretation of the value is determined by the way hardware and software use their bits. E.g., the string of bits could represent alphabetic character, a string of characters, an integer, audio recorded, maybe a song, a video, depending on what you're representing. In addition to items, computer programmer understand computer hardware can be designed in which set bits can represent status of the 3 peripheral devices. A good example is maybe one can represent maybe a keyboard, a joystick, a camera, and a printer. So these are some of the combinations that can be assigned. We've just taken a 64-bit values and 256 possible values for you to be in a position to understand. But something to note is that bits have no specific meaning. All meaning is imposed by the way bits are interpreted. Right? I think so. What does a given pattern of bits represent? The most important thing to understand is that bits themselves have no meaning in strict meaning. The interpretation of values is determined by the way hardware and software use their bits. And I've given a very good example there about a string of bits could represent specific characters, an integer, a floating point, a computer program, etc. So it's the interpretation that matters. So a very good question is binary weighted positional representation is something that you find around. So one of the most common abstraction used to associate a meaning with each combination of bits interprets them as numeric value. E.g., an integer interpretation is taken from mathematics. Bits are values in a positional number system that uses the base 2. To understand the interpretation, remember that in base 10, the possible digits are 0, 1, 2, 3, 4, 5, 6, 7, and 8, 8 and 9. Each position represents a power of 10. And represent a power of 10. And the number 1, 2, 3 represents 10 to the power of 2, right? So in the binary system, the possible digits are zeros and 1, and each bit position represents the power of 2, right? So I think I have an illustration that explains the value associated with each of the 6-bit position when using a positional interpretation in base 2, right? So I've given an example of the binary number and how it is represented. a set of k bits can be interpretation to represent a binary integer when the conventional position notation is used. The values that can be represented with the k bits are range of 0 to 1 and 2, right? Remember, because it's an essential skill in design of both hardware, software and hardware, anyone working in this field should know the basics, the decimal equivalent of binary numbers that the hardware software designer should know. Smaller values in the above table should be memorized. Hardware and software designers only need to know the order or magnitude of the larger entry. So we move on. That one, if you internalize it, you're going to understand it better. This is a summary of what you need to know. So we move on to something referred to as the bit ordering. On the above or the previous table, we have discussed we have seen the positional notation. When writing a decimal numbers, we always write the least significant digit on the right and the most significant digit on the left. Therefore, when we write in binary, it makes sense to write the least significant bit on the right and the most significant bit on the left. So when digital logic is used to store an integer, however, the concept of the right and the left no longer makes sense. Therefore, a computer specialist must specify exactly how bits are stored and which are the least and the most significant. Right? I think that's a very important element to take note of. So the idea of bit ordering is especially important when bits are transferred from one location to another. E.g., when a numeric value is moved from a register to the memory, the bit ordering must be preserved. This is mostly when sending data across the network. The sender and the receiver must agree about the bit ordering so that the message can reach us as it is sent. That's very good to take note about the LSB and the MSP and the agreement between different the sender and the receiver. So we move on to something referred to as the hexadecimal notation. A binary number can be translated to equivalent decimal number. Programmers and engineers sometimes find the decimal equivalent difficult to understand. E.g., if a programmer needs to test the fifth bit from the right using the binary constant, which is 00000, make the correspondence between the constant and the bit much clearer than the equivalent decimal constant 16. So the long strips of bits are unwittingly difficult to understand as a decimal equivalent, e.g., to determine the sixth bit is set in the following binary number and the human needs to count individual bits. So making it a bit making it a bit difficult, right? So to aid the human in expressing the binary values, a compromise has been made. A compromise has been made or reached for positional numbering system with a larger base. If the base is chosen to be the power of 2, translation to the binary is trivial, and the base 8, known as the octal, has been used, but the base 16, known as the hexadecimal, has become very popular, right? So, in essence, hexadecimal encodes each group of 4 bits as a single as a single hexadecimal between 0 and 15, right? And the figure below, or the figure gives the example of how the uppercase between A and F to represent the hexadigital digits above 9, right? So some programmers and some programming languages use the lower case letters A and F instead of the distinction, which is quite important. So you can see. So the 16 hexadecimal digit and the equivalent binary and the hexadecimal values. Each hexadigit encodes the 4 bits of the binary variable. I've represented that, and also another representation of how a binary string corresponds to the hexadecimal equivalent. I've explained it here. So this is the relationship between the binary and the hexadecimal. Each hexadigit represents 4 bits. So the digits used in binary, decimal, and the hexadecimal number system overlap constant and can be ambiguous. To solve the ambiguity, and alternative notation is needed, right? This is how it's represented, and if you have a challenge, you can search more. You can study about the notation for hexadecimal and the binary constant, because the digits used in binary, decimal, and the hexadecimal number system overlap. That's something very important, and sometimes can be a big word for you. But in an ideal situation, to solve the ambiguity, an alternative notation is used or needed. So a computer tend to have the hexa constant begin with the prefix 0x and the binary 0b, and the notation of 135 to the power of 16. All right. So that's it. I've been a bit straight to the point. The other one is the character set. The character set. A computer system defines a character set to be a set of symbols that the computer and the input-output devices agree to use. A typical character set contains an uppercase and the lower case letters, digits, and punctuation mark. Previously, we said that bits have no specific meaning, and that the hardware or software must determine what each bit represents. More important, more than one intersection can be used. A set of bits can be created and used with one interpretation and later used with another. So, character data that has both numeric and symbolic interpretation. Each computer system defines the character set to be the set of symbols that the computer and input devices agree to use. A typical character set contains the upper and lower letters, digit, and punctuation mark. A computer architect often chooses a character set such as each character fits into a byte. A computer that uses an 8-bit and 256, that's 2 to the power 8 character in its character set. A computer that uses 6-bit that has 64 to the power of 6 characters. The relationship between the byte size and the character set is so strong that many programming languages refer them as the byte as the character. Yeah. Right? What bit values are used to encode each character? You see, that's the big question, because depending on the computer or the character set that you have, you have to know what bit values are used to encode each character. So the computer architect must decide between maybe a specific system or what. So in 1960, for a good example, IBM Corporation chose the extended binary coded decimal interchange code, abbreviated as EBCDIC, in representation as the character sets used on IBM computers. CDC Corporation chose a 66-bit character set for use on the computers. The two character sets were completely incompatible, right? A computer system connects to devices such as keyboard, printers, modems, and other peripheral devices. Had to use a specific peripheral devices for a specific system. So, to help vendors build a compatible equipment, the American National Standard Institute defined a character representation known as the American Standard Code for Information Interchange, which is the ASCII character set that specifies the representation of 128 characters, including the usual letters, digits, and punctuation mark. Additional values in an 8-bit can be assigned for special symbols. The standard is widely accepted, right? So I think there's somewhere I'll be posted. You can just go online and check the ACSS, the character set, and each entry of hex values. It's available online when you just try to Google that. So we can move on. In other cases, the computer programmer extends the character set to accommodate other people, like the people who did not use the ACII character set, mostly the Chinese and people from the Far East. So there was the introduction of a Unicode that was an extension of ACSS. So although a 7-bit character set and 8-bit work well for English, some people from the Far East were disadvantaged, and that's why we had the introduction of a Unicode that really helped the people from the Far East to help in their larger representation. So all said and done, I think we have been a bit brief. We don't want to discuss so much, but I need to just summarize about the whole thing. What we've discussed: the underlying digital hardware has two possible values, right, which we say the logical 0 and the logical 1. Whenever we think of two values as defining bit, which is the binary digit, and use bits to represent any program or software, each computer defines a byte size, and most current systems use 8 a set can be used to represent a character from computer. A set of bits can be used to represent a character from computer character set, and signed integer, a single or double precision floating point value, or a computer program. Organizations like ANCI and maybe the EEE have created standards to represent to help in hardware manufacture by having a standard character set. So with that, I think we will be coming back and discussing more about a few programming languages and the binary coded decimals, but that's a summary and a very straightforward way of thinking. So thank you for your time. See you on our next video.